Okay, so thank you again for the presentation and for organizing this first neuroimaging webinar. As Antti said, I'm a neurologist working currently at the Queen Square MS Center, where my main research interest is to develop imaging biomarkers directly linked to the pathological processing underlying demyelination in different inflammatory disease phenotypes. So, as you all know, in the last decade, MRI has emerged as a fundamental imaging biomarker for MS. And over the last years, development in brain and spinal cord imaging acquisition and post-processing have made a huge contribution to our understanding of disease-specific pathogenic mechanisms, not only for the diagnosis of MS, but these advances are important also for the differentiation between MS and other inflammatory diseases of the central nervous system. In particular, between MS and the other two well-known antibody-mediated inflammatory diseases of the central nervous system. Relapsing-remitting MS, aquaporin 4 antibody, neuromyelitis optica spectrum disorder, and MOG antibody disease are different inflammatory diseases characterized by different pathobiological mechanisms. In fact, neuromyelitis optica spectrum disease is characterized by the presence of antibodies against aquaporin 4, which is present on the food processes of astrocytes. And MOGAD is characterized by the presence of antibodies against myelin oligodendrocyte glycoprotein, which is a CNS-specific protein located in the outer layers of the myelin sheath. However, these three diseases share clinical features, thereby posing diagnostic challenges, in particular at the disease onset. It is important to differentiate between the three diseases because treatments are different. MRI is one of the most attractive and widely available diagnostic tools, and over the last few years, similarities and differences in the MRI lesional features between the three diseases have been identified. In particular, if we consider brain MRI, in MS we typically are used to see these the typical Dawson fingers lesions, which are those lesions perpendicular to ventricles. In NMOSD and MOGAD, brain MRI can be unremarkable or show lesions which, for example, in NMOSD can be located periependymal surrounding ventricles, or in MOGAD, the lesions can be ill-defined, large, and with a leukodystrophy-like aspect. In particular, MOG antibody-associated demyelination manifests with an age-related phenotype. It has been demonstrated that children with MOGAD present with a severe leukoencephalopathy phenotype in the very young and normal intracranial MRI in the older children. Also, the announcement can be different and can help differentiating the three diseases. Being in MS, lesion have a characteristic nodular enhancement, while in NMOSD the enhancement can be cloud-like. In MOGAD, there are highly contrast-enhancing lesions. As I already mentioned, brain MRI in NMOSD and MOGAD can be normal in patients with optic nerve and spinal cord involvement. But also we can see differential findings using a conventional MRI scan, also on the optic nerve. In MS, the optic nerve is involved more anteriorly with the short-length lesions, while in NMOSD, the lesions involve mostly the posterior part of the optic nerve and the chiasm. In MOGAD, the involvement of the optic nerve tends to have unique features such as bilateral simultaneous optic nerve involvement. What about the spinal cord? So in multiple sclerosis, lesions are typically small, short, involving less than one vertebral segment or less than 3 vertebral segments in particular, and can be multiple and asymmetrical. Neuromyelitis optica spectrum disorder is characterized by the presence of a longitudinally extensive transverse myelitis spreading over at least 3 vertebral segments, and cervical cord is the most involved part of the spinal cord involved in NMOSD. While in MOGAD, there is the longitudinal extensive transverse myelitis often affects the lower thoracic cord and the conus rather than the cervical cord. Using conventional MRI, the Manims group has previously proposed the following MRI criteria based on brain lesion distribution and shape that can help to distinguish MS from aquaporin 4 antibody NMOSD. More recently, another multicentric European study led by the group in Milan have proposed the following new MRI criteria to identify both seropositive and seronegative aquaporin 4 neuromyelitis optica spectrum disorder from MS. However, none of the seronegative patients in this cohort was MOG antibody positive. It will be good and useful to identify MRI criteria to distinguish MOGAD from the other two diseases. And this will be the main aim of a project that I'm going to carry out soon, supported by the Manims European Network, and that will involve the collaboration between UCL in London and University of Siena. So we have seen that conventional MRI is helpful in differentiating the 3 diseases, but we know that the application of non-conventional MRI techniques may in general increase our knowledge about the mechanisms involved in diseases. However, today, only a few studies have been published on MOGAD. So I would like to discuss with you about potential future biomarkers in MOGAD, starting with MRI features that have been demonstrated already to help the differentiation between MS and aquaporin 4 antibody NMOSD. So let's start with the central vein sign. This is, the first work that I have carried out here at Queen Square, looking at the potential value of the central vein sign to distinguish MS from aquaporin 4 antibody NMOSD using a clinical 3T scan. So we have identified lesions on PDT2, and then the mask of the lesions was registered on the SWI. And each white matter lesion was assessed to look for the presence of the vein, either as a dark line coursing through the lesions, as you can see here, or as a dark dot trapped on contiguous slices. What did we find? We found that the central vein sign was present in 80% of the lesions in relapsing remitting MS, while it was detectable in 32% of the NMOSD lesions. In addition, we also found that the presence of at least 54% of white matter lesions with a central vein sign predicted a diagnosis of MS with a high accuracy, high sensitivity, and high specificity. On SWI, it is also possible to detect a rim surrounding the lesions in MS, which is thought to be a sign of iron deposition. This rim is not visible in NMO lesion. Well, another important finding that on MRI, on particular sequences on MRI can distinguish between MS and NMOSD is the presence of cortical lesions. So cortical lesions are recognized as present in MS, and they have been recently included in the new diagnostic criteria for MS, but they are absent in NMOSD. What happened in MOGAD? So to date, we only have a few case reports reporting the presence of cortical lesions in the acute phase of patients with an onset characterized by epileptic seizures. But we don't know today what happened in the chronic phase and if they can distinguish between MS and NMOSD. So in addition to the inflammatory lesions visible on conventional MRI sequences, demyelinating diseases cause neurodegeneration and consequent brain and spinal cord atrophy. There seem to be differences in the patterns of atrophy between MS and aquaporin 4 antibody and NMOSD. MS patients showed more brain atrophy, mainly in the gray matter, than NMOSD and anticontrols. It is unknown whether MOGAD also different in terms of brain atrophy. But also in this case, there is only, there are no reports published to date. This is the case of a patient that we have seen at Queen Square, a young patient, 19 years old, who had the onset when she was 10 years old with seizures. And she was initially diagnosed with relapsing remitting MS and then treated with therapies for MS. And then she kept having several relapses until she came and we tested her for the MOG, and she was found to be MOG antibody positive. Well, in this patient, we can see that there are lesions, periventricular lesions involving the U fibers and sparing the corpus callosum. And on PSIR, we can also see that there were a lot of juxtacortical lesions with focal atrophy, making us thinking that something happened in the as an atrophy in the brain of MOGAD patients. But when we talk about gray matter, we should also consider deep gray matter. In fact, Arman and Shaggy here at UCL has shown using machine learning approaches that deep gray matter imaging biomarkers automatically obtained from clinical scans can be used to distinguish NMO from MS. Since spinal cord is a very eloquent site of pathology in MS, spinal cord atrophy has been considered in multiple sclerosis as an exploratory outcome measure in clinical trials, especially in patients with progressive MS. Recently, only one study has investigated spinal cord atrophy in MOGAD and found that the cervical cord area was decreased in aquaporin 4 antibody and NMOSD, but not in MOGAD patients when compared to healthy controls. And there were no differences in cord atrophy between the two groups of patients. Studying the spinal cord means also trying to apply advanced MRI techniques to the spinal cord to look at the microstructural changes. This is a study undertaken by Professor Ciccarelli, who showed that lower myoinositol creatine values using spectroscopy suggesting astrocytic damage were consistently found within the NMO lesions when compared with healthy controls and patients with multiple sclerosis, who showed at least one demyelinating lesions at the same cord level. And also the application of advanced protocol like diffusion techniques may have the potential of detecting microstructural changes also outside the lesions. In this study, looking at the spinal cord of primary progressive MS patient and applying a Q-space imaging, which is a diffusion technique, Abdelaziz found increased indices of perpendicular diffusivity in the patient group when compared to controls. This perpendicular diffusivity, increased perpendicular diffusivity indices, were found also consistently present after 3 years in a follow-up study with the same cohort. So it will be interesting to look at MOG antibody disease to see, to check what happens in the normal appearing white matter or normal tissue in this group. Finally, the optic nerve. The optic nerve has shown a potential to be used as a biomarker in these diseases, which usually affect the optic nerve, and in particular OCT. To date, there are some reports showing alteration in OCT in MOGAD, which, however, are less evident than aquaporin 4. And in this study in particular, not only the OCT measures, but also the axial lesion length in the acute phase of the two diseases was studied and was found to be a strongest predictor of visual prognosis in aquaporin 4 optic neuritis, but not in MOGAD. So to summarize, what can be the application of non-conventional MRI techniques in the different emulating diseases, and in particular in MOGAD, where we have seen that only a few reports have been published to date. So, first of all, the application of automatic brain and spinal cord lesion detection tools can help us to investigate the spatial patterns of brain and spinal cord lesions in MOGAD, to discover new lesional features which can predict MOGAD and improve the differential diagnosis. Then we can also look at specific characteristic features such as cortical lesion and the central vein sign, as well as identify differential patterns of atrophy in the brain and in the spinal cord. In the spinal cord, the application of non-conventional MRI techniques such as diffusion can help to look at the microstructural pathological signatures of the three diseases, and also the study of the optic nerve can add useful information. So I would like to thank you everybody for your attention, and thanks all the group working at the NMR unit between like doctors, physics, engineers, nurses, everybody, and in particular my supervisor, Professor Ciccarelli, who is, I think, one of the example of the women working in MS, giving a huge contribution to MS research. Thank you.
Okay, thank you, Rosa, for this really comprehensive and very, very nice overview of what is known so far regarding MRI features of these three different disease types, subtypes of MS, or probably not anymore considered subtypes of MS. So it's a really important work, I think, to do to better characterize the differences on MRI between these disease types. Are you also intending to look at the cerebellum? Because I know that there has been work before in NMO compared to MS, where it was found that the cerebellum is actually not affected in NMOSD on MRI. Are you actually planning to look at this as well?
Yes, we are going to look also at the cerebellar, in particular in terms of atrophy.
Mm-hmm. Great, yeah.
And to look at differential features of atrophy in the cerebellum as well.
Okay, perfect. Okay, are there any questions from the audience? And please just remember to unmute yourself if you want to speak. Not so far. Okay. So.
Okay. Thank you very much.
Yes, thank you very much for this nice talk, and we wish you a lot of success with this project. It's
thank you.
super interesting. Looking forward to the results.
Yeah, some of them will be presented at ACTRIMS this year.
Nice, great. We're looking forward to that, and we're all coming to here to your talk.
Okay, thank you. Bye.
Okay, thank you. So our next speaker will be Dr. Burkus Saidan from the Mayo Clinic in Rochester. And I'm just trying to unmute her first because she's still muted. And also,
can you hear me now, Angie?
Yes, I can hear you now.
Okay, good.
Perfect. And you are able to share your screen now. So Burkus Saidan is, as I said, working at the radiology, at the neurology department at the University of in Rochester, the Mayo Clinic in Rochester. She's an assistant professor of radiology there. And she is a research associate at the Division of Neuroradiology. She received her MD degree and also subsequently completed her residency training in the Department of Neurology at Istanbul University. So we're really happy to have this diversity in our speaker series today. Her research focuses on imaging and epidemiology of demyelinating and neurodegenerative diseases, and we're happy to have you here. She's also one of our group leads of this neuroimaging interest group, and with this, I just want to give the word to you to start.
Okay. Thank you for the introduction, Anche, and I would like to thank all the participants for their interest in this first neuroimaging webinar. I will talk about CRISPR compound B PIP-PET imaging in MS. Can you see my slides?
Yes, we can.
Okay, good. So first, I will talk about our study on PIP-PET white matter imaging in an aging population, and then I will talk about our second study, which is an investigation of white matter PIB uptake as a marker of white matter integrity. So let's start with a brief background. Cortical beta amyloid plaques are one of the pathological hallmarks of Alzheimer's disease. And CRISPR compound B, PIP, which I will refer to as PIP from now on, it binds to fibrillary beta amyloid with high affinity and quantifies cortical beta amyloid plaques. So here are two scans. We see two images. The one on the left is a normal scan, and the one on the right shows high cortical PIB uptake, which we usually see in Alzheimer's disease patients. So PIP-PET imaging is used frequently in dementia. However, little is known about PIP-PET imaging in aging MS patients. Advanced MRI techniques such as diffusion tensor imaging are used in imaging myelin of brain parenchyma, but they are not myelin specific. And there's a growing interest in white matter imaging with PET. Amyloid tracers such as PIP are recently shown to target white matter. So our objectives in the study were to investigate the association of PIP binding with cognitive function in an aging population and to investigate white matter PIP binding as a potential myelin marker in, again, an aging MS population. We studied the individuals enrolled in Mayo Clinic Study of Aging, MCSA. It is a population-based study of cognitive aging. And we started with 4,869 participants. 24 of them were diagnosed with MS using the most recent diagnostic criteria. And 16 of these 24 had brain MRI. 12 of the 16 also had PIP-PET. So we evaluated these participants for psychological testing, MRI, and PIP-PET. The neuropsychological battery assessed 4 cognitive domains, which were memory, language, attention executive function, and visual spatial skills. And then a global cognitive disease score was also calculated. With the 3 Tesla MRI, we evaluated the cortical thickness and thalamic volume. And with PIP-PET, we looked at white matter lesional and normal appearing white matter PIB uptakes, which were evaluated using the standard PIB uptake value ratio. Now, here are the participants' characteristics, the demographics table. Each MS patient was age and sex matched to 5 controls. Education, ApoE4 carrier status, and short test of mental status were not different between the groups. However, when we look at the domains, we see that memory and language was cognitive Z-scores were lower in MS patients compared to controls. Now here are the MRI findings. As expected, MS patients had higher white matter volume than controls. Looking at cortical thickness, we see that frontal and temporal cortical thicknesses were lower in MS patients compared to controls. And MS patients had also smaller thalamic volumes than controls. And this is in line with the thalamic atrophy shown even in the pre-symptomatic stage of the phase of the disease, which is radiologically isolated syndrome. And these box plots again demonstrate the significant difference in thalamic volumes in these two groups. Now, moving to pipette findings, I would like to start by showing some example scans. These are individuals with gradually decreasing white matter hyperintensity load, but similar global cortical PIB-SUVR. The first one is an MS patient, a 65-year-old man with MS and with additional white matter hyperintensity risk factors of smoking, dyslipidemia, and coronary artery disease. On T2 FLAIR, we see typical demyelinating lesions which appear as T1 hypointensities and MPRH as black holes. And now looking at the PET images, we see that there seems to be almost no PIB uptake in these lesions. Looking at the second example, this is a control participant who is the same age, 65-year-old woman, again similar white matter hyperintensity load, without MS but with white matter hyperintensity factors of hypertension, dyslipidemia, and obstructive sleep apnea. So we see these high T2 hyperintensities on T2 FLAIR image, and again corresponding T1 hypointensities, which seems to be less prominent. And again in the PET image, there is reduced PIB uptake of the same lesions, but again less prominent compared to the MS patients' lesions. Now looking at the data with box plots, we see the comparison between PIB-SUVR in normal appearing white matter and white matter hyperintensity in two groups, controls and MS patients. First, let's look at the normal appearing white matter compartments. Although not statistically significant, PIB uptake was lower in the MS patients compared to controls. Similarly, in the white matter hyperintensity compartment, PIB uptake was again lower in the MS patients compared to controls. And overall, we see that there is a decrease in PIB uptake going from normal appearing white matter compartment to white matter hyperintensity compartment and from control to MS. Now, looking at the results within the groups, in controls, we see that the PIB uptake is lower in white matter hyperintensities compared to normal appearing white matter, and it is statistically significant. Similarly, in MS patients, the PIB uptake is significantly lower in white matter hyperintensities compared to normal appearing white matter. Now, taking it to the further step, we also look at the white matter PIB uptake association with cognitive function. And we found that reduced PIB uptake in areas of white matter hyperintensities was associated with decreased visuospatial performance in MS patients. To conclude the first study, in aging MS patients, we see reduced cognitive performance and cortical and thalamic atrophy, which are expected. And for PIPET, we can say that it may be a potential measure of white matter injury, and it reflects the injury to largest white matter network connectivity, such as those involved in visuospatial performance. So this is the first study about PIPET in MS, and taking into account our second conclusion from the first study, we continued with the second one, where we looked at in further detail the white matter PIB uptake as a marker of white matter integrity. Again, I'm going to start with a little bit of background. In previous studies, it has been observed that PIB uptake is lower in white matter hyperintensities in older adults. And it has also been observed that PIB uptake is lower in demyelinating white matter lesions in patients with multiple sclerosis, including our current study that I presented. And based on these studies in multiple sclerosis showing lower white matter PIB uptake, it was thought that PIB binds to the beta-pleated sheet of myelin basic protein in the white matter. These findings are from animal studies and also human studies. Therefore, it was suggested that white matter PIB uptake is a potential marker of white matter integrity. So I will mention a previous study by our group where we showed that white matter PIB uptake increased with age gradually in a large cohort of unimpaired older adults, both in periventricular white matter and subcortical white matter. And our objective of the second study was to investigate the basis of PIB uptake in white matter hyperintensities and normal appearing white matter. We know that fractional anisotropy and mean diffusivity, FA and MD, in DTI are well-known imaging biomarkers of white matter integrity, but as mentioned before, they may not be myelin specific. So we studied the associations of white matter PIB uptake with FA and MD, and also the associations with global cognitive function, this time in cognitively unimpaired older adults. Here are the participants. They are again from the Mayo Clinic study of aging. It is a population-based study. And our participants were cognitively unimpaired adults within an age range of 65 to 95. And we investigated the participants who underwent PIPET and an MRI that included a DTI scan. And the global cognitive function was calculated from each participant calculated on each participant from 9 cognitive tests. An overview of our analysis, PIB-SUVRs in white matter hyperintensities were compared to the normal appearing white matter. And MD and FA in white matter hyperintensities were compared to normal appearing white matter within subjects. We also looked at the correlation with age for each measurement. And we also studied the correlations between PIB and FA, PIB and MD in both compartments, in the white matter hyperintensities and normal appearing white matter. And since, as I showed our previous findings, since age may influence this relationship, we adjusted the correlations for age. These are the participants' characteristics. We had 537 cognitively unimpaired older adults from the Mayo Clinic study of aging. The average age was around 76 with a slightly higher percentage of men. And again, as expected, white matter hyperintensity volume significantly increased with age. Here are the results comparing PIB-SUVR, FA, and MD in both compartments. As you can see, the PIB-SUVR in the white matter hyperintensities was lower compared to normal appearing white matter. in line with what we found in the MS patients. The FA was lower in white matter hyperintensities compared to normally appearing white matter, and MD again was higher in the white matter hyperintensities compared to normally appearing white matter. Now, correlating with age, we found that in both compartments, PIP-SUVRs increase with age, FA in both compartments decrease with age, and MD increase with age in both compartments. Here are the plots of associations of PIP in the y-axis, and FA and MD are on the x-axis. The white matter hyperintensities are shown in black, normal appearing white matter in red. Lower, here we see, because there was a relationship between the imaging measures and age, as I have shown in the previous slide, we adjusted these correlations with age. And after adjusting for age, we found that in white matter hyperintensities, PIP-SUVR correlated with FA, but not in the normal appearing white matter, and lower PIP-SUVR correlated with higher MD in both compartments, both in the white matter hyperintensities and normal appearing white matter. Looking at the association of PIP uptake with global cognitive function, we found that in the white matter hyperintensities, lower PIP-SUVR was associated with lower global cognitive function. And similarly, in normal appearing white matter, again, lower PIP-SUVR correlated with lower global cognitive function Z-scores. To conclude the second study, in the white matter, correlations of lower PIP uptake with lower FA, higher MD, and lower cognitive function suggest that reduced PIP uptake in white matter may be associated with loss of white matter integrity. With that, I would like to thank my mentors, my co-investigators, and of course, I want to acknowledge funding, and I'm happy to answer any questions. Thank you.
So yeah, thank you. Burcu, this was a really nice talk, and it's a very comprehensive project that is actually taking into account a lot of different modalities. This is really nice to include the PET and multiparametric imaging data like the diffusion data. Are there any questions from the audience? And please don't forget to unmute yourself. There are any? None so far. Okay, yeah, I think this is a really important work and field of study that is certainly understudied, especially as you are looking, as far as I understand, at patients who are older, right?
Yes, these patients are older because they come from Mayo Clinic study of aging, and now we have younger participants starting from 30 year of age, but in order to see these changes in PIP uptake, we focus more on older participants because as they age, they tend to have more PIP uptake. And in the dementia field, it's more of an off-target phenomenon, the white matter PIP uptake. But it seems there is now interest in the MS area for this. PIP and other compounds in PETs may seem to be it seems to be binding to or showing changes in white matter integrity.
Mm-hmm. Yeah, this is very, very interesting. So yeah, thank you very much. Is there any?
Thank you.
Yeah. Is there any?
Sorry, I'm Georgina, but I was checking. There's a question in the chat of someone who doesn't have a microphone. Jane Turk.
Oh, Jane, I see. Let's see. I can actually unmute her. So now, Jane, I think you should be able to speak now. because you're unmuted. Now you're.
I think I see the question. So
I
she
don't have a microphone, so maybe somebody can just read the
yeah, I see the question. She asks about did you look at whole brain atrophy in your first study, and what cognitive tests did you use? So we have the data. We can look at the whole brain atrophy, but we focused on cortices in like frontal, temporal, parietal, occipital, and for what was interesting was that the temporal lobe, which had the higher amount of cortex in it, was affected in MS patients along with the frontal lobe. And for the second question, which cognitive tests we used, so we had a neuropsychological battery, and as I said, we evaluated 4 domains. I can tell you which tests we used, but we also have it in our supplement in the paper. But generally, quickly, I can say like for the language, we used the Boston naming test and category fluency. For memory, we use the logical memory, visual reproduction, and auditory verbal learning tests. For visual spatial, we use the picture completion and block design. And for executive, we use the trail making test B and digital symbol substitution test. But as I said, there are more detailed informations in the supplement of the paper.
I had a question. This is Corey. Hopefully you can hear me okay.
Yeah,
in the first study, you had a slide that showed just visually the different PET images from I think 4 different subjects.
Yeah.
If you can go back to that, that would be.
Yeah, I'm trying to. Yeah.
So
yeah, this one.
So here, so I was just noticing, like in some of them, like the second row or even the first row, there seems to be these focal increases of the PIB. I'm assuming the yellow is high in areas that don't look like they necessarily correspond to lesions or anything. So I'm wondering about that, if that's of any significance, or is that just kind of noise? And also, do you see any signal from the gray matter at all, or is that masked out?
So I didn't give more details about the methods we used. I had a slide for the second study about how we analyze the data. I can actually go to that slide that
okay, sorry, maybe I missed that.
Let me just. So I had the slide about how we did the analysis and acquisition. So as I said, we performed the MRI at 3 Tesla, and it includes FLAIR and MPRH. First, the FLAIR was registered to T1 weighted MPRH, and then MPRH was segmented to generate a white matter mask. Here, what we did was the white matter mask was eroded by 3 voxels, so that to exclude the voxels affected by partial volume averaging of gray matter and cerebrospinal fluid. I think it answers partially your question about the gray matter. And so that the immediate periventricular white matter and the U fibers were not included in the mask, then we have a semi-automated algorithm to segment the white matter hyperintensities and normal appearing white matter and FLAIR. And through the segmentation, we had 2 subclass masks, a white matter hyperintensity mask and a normal appearing white matter mask. what I'm trying to say that the gray matter may bleed into the white matter, but as we erode it, I think we were able to limit this potential effect.
Okay, and then the focal increases that you see in the white matter,
in those images, they might be non-specific. So I can look at them individually, because we looked at the PIB uptakes in those lesions, and they were qualitatively okay. Looking at them, we see that there's almost no PIB uptake, but also quantitatively, we know that these A1, A3, A2, they had lower PIB SUVRs compared to B1, B2, B3. But I know you're asking about the yellow ones, areas. I don't have measures for them, but I can look at them.
I'm just curious if that was something that you guys noticed or kind of looked into. It looks very interesting.
Yeah, we mostly focused on the lesions and how there is almost no uptake in those.
Okay, thank you.
Thank you for your question.
Okay, any other questions from the audience? So obviously none anymore. So with this, I want to thank you again, all the two speakers. This was really great for their contributions and for being so courageous to be the first presenters of our series. And thank you to Burcu, who just jumped in spontaneously, as we just had one speaker and we wanted to have two. I'm sure both speakers will be available by email if you have any further questions. For those of you who have joined along the way, I would like to briefly repeat the concept of the webinar and how we imagine to go ahead. We generally want to encourage everyone in the audience or any colleagues you know who would like to give a talk, and we want to be as inclusive as possible, which means that we include women and men as long as they embrace our goal to foster diversity and increase female representation in the MS research community. We would also like to encourage more senior researchers to give talks, as the format of these online conferences is to have both junior and senior speakers. And by the way, we also want to encourage more researchers to join our neuroimaging interest group or any other of the interest groups. There is a lot of people that have joined IWIMS, but they have not specifically joined interest groups. So I really want to encourage everyone to do that. Regarding the format of the webinars, we will have 2 to 3 talks of about 12 to 15 minutes each, with time for a couple of questions after each talk. As we are learning along the way, we would really appreciate your feedback on how we can improve. Regarding future webinars, we're planning to schedule about 1 every 3 months. So the next one will be around the beginning of November. And I want to encourage everyone to get back to either Cory, Burcu, or me if you would like to give a talk. The webinars will always be advertised on the IWIMS website under the section of Global Scientific Meetings, as this one was as well. You will also find the link to the upcoming webinars and a video of it afterwards, granted the permission of the speakers. And you will find a video of this one because both speakers have actually permitted us to put this video online after the webinar. We also want to thank all the audience for joining us today in this really exciting first inaugural webinar, and of those who will listen to this seminar anytime in the future, for the interest in our group, in the work of our speakers, and also in their support of promoting women in research of MS and hopefully also in other domains of research. And with this, I think I would like to finish this webinar, unless Burcu or Cory, our co-leads of this interest group, would like to say anything that I forgot to mention.
I think you mentioned everything, and I'm very happy with this interest in our first webinar. Thank you for the participants for their interest. And yeah, is there anything you want to say, Cory?
Nope, I have nothing to add. Thank you, everybody that participated. Next time, 3 months roughly from now, tell all your friends and we'll get even more people. But it was great to see all the names on the side, and I've been chatting with people, so thank you very much.
Great, thank you so much. And I apologize, the beginning of the webinar, which is just my very unimportant introduction that I repeated at the end, is not recorded. I just started the recording with the talks. But next time I will be better in that. And again, thank you so much for your participation, and we hope to see you at one of the IWIMS meetings that take place usually with the big conferences, either the AAN or with the ACTRIMS conference. The next one is upcoming in Stockholm. So I hope to see many of you there, and I hope to see many of you in the next webinar. And with this, I hope you have a good evening, night, or whatever is upcoming for you. Bye-bye.